other person qui vont le point. Okay. Hello everyone. Thanks everyone to being there. So I will present you the work I'm doing in my PhD. So Mohamed Amine Legheraba. I'm a third year PhD student in physics at Sorbonne University. And my supervisor are Maria Potov, and Sebastian Tixay. And I'm working on peer-to-peer network on the decentralized machine learning. So a bit of context. So I think you now with ChatGPT, and I think everyone know a bit about supervised machine learning, especially for classification. The idea that we have a lot of data, and each data point is has a label. For example, for the binary classification, the Spain-based database, we have a bunch of emails, and the emails are either normal emails or spam. So we want a way to predict if an email is spam or not. So what we do is that we have a database. We have a database of emails, and for each email we have some feature. For example, here we have some of the features, so the frequency of some words, and we will try to learn an algorithm to determine based on the feature if an email is spam or not. And the goal is to obtain something like this at the left. So we have here we only have two features, but of course in reality it's multidimensional, and the algorithms can classify the emails are the spam or not. And if we have a new email that has not been labeled, we can predict the future lab. And for this case, it's very simple, it's binary. But of course, the most complex case, for example, with the MINT database, we have a picture of number, and we want to predict the number, the number of the picture. And so we can do this supervised machine learning in a centralized way. So we gather all the data and we run the algorithm, and at the end we have the trained machine learning algorithm, and we can use it to predict new data. But so in some cases it's not feasible. And before talking about the decentralized case, I want to talk about two main notions. So the first one is online learning, and the second is ensemble learning. So the idea of online learning is that we can imagine that we don't have all the data at the beginning. We receive data as a stream. So imagine we want to predict the weather. So each day we receive the new weather of the day, and we want to improve at each step the predictor. So one algorithm that is suitable for online learning is gradient descent. So to improve the accuracy of the predictor, what we do is to compute the gradients or the derivatives of the function that we want to optimize, and we take the previous value of the parameter, and we decrease the value with the value of the derivatives. And thanks to this, we can converge to the optimal version of the parameter for the machine learning approach. And the second idea, ensemble learning, is that we can imagine that we have a lot of weak models. So maybe this model is not very good at some prediction, but we can aggregate a lot of weak models to create a strong machine learning model. And for example, we have the random forest algorithm, which is an aggregation of lots of decision-tree algorithms, and the decision-tree are weak linear, but when we combine a lot of weak linear, we can obtain a stronger linear algorithm. And it's this two ideas that we use for federated learning. So the idea there is that instead of having all the data in one server, we have a lot of clients in our network, and each client will compute a machine learning model based on his own local data. So he can create a model, but this model will not be very good because it only learned on his own local data, and maybe he has only a few data points. But we will aggregate all the models in a central server, and the central server will create the global model. So it's like in ensemble learning, what we have is strong linear algorithm from weak models, and we will send back the new version of the model to the clients. And like in one online learning, we will do several steps of training until we converge to good models. And thanks to these two concepts, and thanks to federated learning, we can have this system where we don't need to aggregate the private data. Each client can keep his private data locally, but we only send the models. But at the end, we can have this machine learning model that is efficient, that we can use for prediction. So to give a small example, imagine that you have picture on your phone. You don't want to share your private picture with your friends or with the central server, but you want to have an algorithm that can predict if there is a face on the picture, for example. So what you will do, you will train the models on your local pictures, but because you only train on your own picture, you don't have a lot of pictures, or maybe all the pictures are mostly the same, or very like each other. But if a lot of people do the same things and we aggregate all the models, we can at the end have a strong predictor, but we don't need to share our data. So this is federated learning. It was proposed in the literature, I think almost 10 years ago, and it's already used in some cases, but we still need this central server for the aggregation. So for the algorithm, so as I said, each client will compute a model based on his own data, and it will send the model to the central server, and the central server will aggregate all the models. So the aggregation, it just means that the server do the mean of all the model it received, or the mean of all the parameters, and it sends back the new model to the client. And as I say, the problem is that we still need the server. And if the server is down, we cannot continue the aggregation. So one alternative for this, one alternative that is totally decentralized and that work on a peer-to-peer network is gossip learning. And the idea is that we are in a peer-to-peer network. Each node in the network is connected to other nodes in other fashion, so everyone can create connection as he wants, and we can imagine that each node has the address of other nodes in the network and can communicate with them. And what each node will do is that at each period of time, it will select one of his neighbors at random, and it will send to him its own model. And we have a background process. Each time a node receives a model from a neighbor, it will aggregate it with his own model and perform an update of this new model on his own data. And so it will have a new model that is the evolution of his own model, previous model on this the model of one of his neighbors. And thanks to this, we can compute, we can converge to a global model that is performant and has good accuracy, good predictions. But this process is very slow, as you can imagine, because we are in a random network where there is no central aggregation. The aggregation is done on the fly, so it's very slow to convert.
Can I ask a question?
Yeah.
So what I'm missing is that when you do these local things and then you exchange data in some way, I mean, so you say that the result is good, but are there any theoretical results which give sufficient conditions for the thing to be, or for the distance between the iterates of these steps and the optimization if you would have the full data? I mean, I'm missing this, just the result on which these ideas rely, the rationale of the discrepancy between the distributed and the centralized. Could you say a few words on that?
Yeah. So if we take very simple model like linear model, we can prove that the aggregation, real aggregation of models assigned from neighbors is the same as having after receiving enough model, the same as having the global model at the beginning. But we can only prove this for very simple linear models because it's linear, it's very simple. For non-linear models like that exist in reality, there is no proofs that I know. But it's what we observe in experimentations. So we observe that when we aggregate enough models, we obtain a good model that have good predictions.
Okay, so there is no guarantee on the discrepancy. So there are cases where it works, and that's it. Okay, right. Thank you. When you mean linear models, it means so you're discussing here multi-layer type things, deep learning or things of this nature. Is that the model in question is linear, or what is linear? What is a linear model?
Like a linear model is just a model that is a linear combination of the features.
Okay, so it's not linked to the learning. It's the model itself.
Yeah, and like you can construct a linear model, but it's not very useful in practice because in practice you want non-linearity in your model because the world is non-linear. So, but for non-linear model, it's very difficult to prove things because when you aggregate, you don't. When you aggregate linear model, it's very simple to prove that the aggregation is the result of the final model is aggregation is the same as if we have the model, the full model at the beginning. But for non-linearity, one non-linear model, I don't know how we can approve it.
And can one hook up, I mean, non-linear models where it fails completely? I mean, what are the type of guarantees? I mean, so since you say that for some models outside non-linear model, outside linear models, there is no guarantee. I mean, how bad can it behave compared to a centralized scheme? So, can you cook up examples where it completely misses the point?
I don't know. I mean, I think it depends also on the distribution of data. Mm-hmm. So in most of the case, we assume that all the peers in the network have the same type of data, so same quantity, same number of labels labeled data, same type of data. So in this case, it's work, but when we have when data is not distributed in the same fashion for nodes, for some models, this aggregation doesn't work, especially for aggressive planning, or it can take more time to do the aggregation. So when you have some discrepancy on the distribution of the data, you need to construct special models to take this into account.
Thank you.
Yeah, so as I said, it's very slow to converge to the global model, to the global model with accuracy. And what we thought is that maybe we need to change the topology of the network to construct a topology that is more suited for this kind of application, so for federated learning, decentralized federated learning. So how we can change the topology in a peer-to-peer fashion. So what I've looked at is about peer sampling. So when you have a peer-to-peer network, you want to have new nodes periodically. You want to exchange with new nodes. But what you can do, the only thing you can do is based on your the data you already have, so your list of neighbors. And for example, here for the proofs algorithm, proof peer sampling algorithm, what will happen is that at each period of time, each node in the network will contact one of his neighbor at random, and it will send to him some of his neighbors as the address of some of his neighbors and its own address. So when for example, one node 4 receive the address of node 1 and from one node 1 it receives the address node 1, node 2, and node 3, the node 4 will send back to node 1 again 3 address from his list of neighbors. So here the address of node 5, 6, and 8, and they will do swap. They will swap this address. So after the shuffling operation, the node 1 will be connected to node 5, 6, and 8, and it will delete the connections to node 4, 2, and 3. And the node 4 will do the same. So it will connect to node 1, 2, and 3, and delete the connection to node 5, 6, and 8. And as you can see, the network remain connected, but each node has new connections. And when you do this several times, you always have random connections, and you always have random representations of the whole network after a few steps. So this was created to ensure that we always have new connections, and even if some nodes are disconnected in the network, you can always connect to new nodes and so on. But in our case, what we want is to have a topology that where we have some nodes that will become central, that they will become hubs, and it's the idea of my work. So I will present two algorithms. So the first is elevator, that is used to create this topology where we have hubs, where we have this node that become like servers, but they were not chosen in advance. They appear at random. And then the heat algorithm, which is the federated learning algorithm that we use for the aggregation. So the idea of the hub-based topology, as I said, is to open a network where we have definite hubs. So the hubs are the nodes that are connected to all the other nodes in the network. And because of this, the distance in the network between any two nodes is 2, because you cannot always connect to the hub to connect to any other node. And any applications that run on top of this topology can take advantage on this. And for example, for the gossip learning or the federated learning, the idea I will present that we will aggregate all the models on the level of the hubs, and so we will have we'll convert quickly to the global model. And for this, I've taken inspiration from the literature in two concepts. So first one is preference and attachment. So in the literature about scale-free network, so this network where we have some hubs in the network, what happens is that each node that connects in the network will connect with preference to the node that already have a lot of connections. And when you do this, you have some nodes that will have a lot of connections, so the hubs, and we have all the rest of the nodes will have a few connections. And also, we also want to maintain some random connection, because if we only connect to the hub, and if the hub are disconnected, the network is disconnected. So we want to maintain some random connections to maintain the connectivity in the network, even in the case of the hub are disconnected.
Just to make it clear, so here each hub is connected to all the nodes. It's not that all the hubs are connected to all the nodes.
All the nodes in the network maintain the address of the nodes in their list of addresses.
Each node is connected to all the hubs.
Yeah. And so for the random attachment, it's the same as described before, the idea of Pearson, decentralized Pearson thing. We want to have the same mechanism or something similar to maintain connectivity, random connection in the network. And so for the elevator algorithm, what we do is that each node will ask all of his neighbors. So each node maintain a list of address that represents the node that he can contact. So when we suppose that if we have the address of the node in the network, we can connect to it. So each node will contact each pair in his cache, so his node list, on which it will send to them a request to receive the cache of the node list of this pair, this neighbor. So each neighbor of the node will send his own cache on list of neighbors, and the node will compute the frequency of all the nodes that appear in the list of all of his neighbors, and it will sort this frequency list, and it will connect with the first pairs that appear in this frequency list. So the idea is that we want to connect to the nodes that are known by all of our neighbors or by most of our neighbors, and we will then ask this list of potential hub or preferred node for a backward connection. So each pair also maintains a list of nodes that have contacted him in the last period of time. And so we receive from each preferred node a random. So each node will when we send the backward request, the hub or the potential hub will send back to us a random connection that it has received. So we will then have this list of random connection, and so we will update the cache, the node list. So we mistake here. It's not random here. It's we will select the edge first node that appear in the frequency list, so the hub, and then we will select random pairs from this backward link. So thanks to this, we maintain after a few cycles, we will obtain a topology where we have the hub. So for example, a small example where we have two hubs, and all the other nodes are connected to this two hubs, so 0 and 1. And all the nodes also maintain some connection to random nodes. And for a real case, for example, I made a simulation with 1,000 nodes, and after a few cycles, we obtain this interval distribution. So for the hubs, we have 10 nodes here, where everyone is connected to this hub, these nodes. And the rest of the interval distribution is look like a random distribution. So we have we have this curve that is centered around the cache minus the number of hubs. So we had an initial cache of 20. That means each node have a list of 20 nodes, and so it's at the end. Each node has the 10th address of the hubs, and the 10 remaining address are a random address. And what is interesting to note is that this is very resilient. So I made some simulation where I made some crash. So at the middle of the simulation, I crashed half of the nodes. So we have 1,000 nodes and I crashed 500, and we still have the same distribution, same form of distribution. But of course, for the crash of half of the node, we only have so in degree for the hubs that is equal to 500, so there's only 500 remaining. And I have also made a test where I have crashed in the middle of the simulation all the hubs. And what we observed that after a few cycles, like 2 or 3 cycles, we have new hubs that operate for the remaining nodes in the network. And there is also the case where we have some churn. And so, for example, it's more visible here from cycle 150 to cycle 750. We remove 10% of the node in the network, and they are replaced by new nodes. So this is the idea that in a real peer-to-peer network, some nodes appear and disappear in a random fashion, and we cannot control if a node will stay connected in the network. So what happened here for the diameter? With the hubs, we should have a diameter of 2, but of course, when we have some churn, the diameter go up because some nodes are disconnected, some hubs are disconnected. But when the churn is finished, the churn period is finished, we go back to a diameter of 2, or almost 2. So that means that our algorithm is a resilience to failure on to churn in the network. Yeah. And so for the second algorithm, so the Hill algorithm, the idea that we will do like the same as in federated learning, but we will use the hubs as a server, so like the server in federated learning. So what happens if the node is a normal node, so not hub, it will choose a number of hubs to send its model, so 1 or 2, and it will send its model to the hubs. When the hubs receive the models from the nodes, they will wait a period of time, and they will aggregate the model received, and then they will aggregate between the hubs. And then each hubs will send the global model to the nodes that have sent to him their model. And each node, when it receives the global model from the hubs, they will also compute the aggregation. If there is no failure, no error, it will receive the same model. So it could also only take, for example, the global model for one app, but we wanted to also think about when the situation is a bit more complex. And yeah, the idea is that we have the network layer. We don't know work on the network layer. We assume that we are on top of a network, and we assume that when we have the address of node, we can communicate with it. And we have this elevator that create this overlay, this virtual network where we have the topology with the hubs. And on top of the elevator topology, we have this hill lightning protocol that I have explained. On top of this application, we can run any supervised learning task. So, for example, the learning task that I explained earlier with the classification. So we made experiments using simulations. So for the peer-to-peer part, I've used the peer sim simulator, which is written in Java. And for the previous experiment with only the elevator algorithm, I have run simulation with 1,000 nodes, but here with the learning part, I have generated a network with 1,000 nodes. And as I say, we have made simulation in a crash-free context, but also where they were in the context of crash. And for the decentralized learning part, we have used the Gossify simulator, which is a simulator made specifically for decentralized learning simulation. And for the machine learning model, we have used small, very simple model like logistic regression and linear. So logistic regression is for binary classification for the space-based database. And linear 5 is for multi, like for classification, for example, for the NIST database where we have multiple labels. And we have compared our result with Federated learning, which is our baseline, and also with Gossify in other decentralized machine learning scale. So for the results, so on top, in red we have Federated learning, which is our baseline, and the second is the most efficient. But at the same time, we only have one server. And for our case of hub learning, which in orange, it's very close to Federated learning. We obtain almost the same results, same time to obtain a good accuracy. And what you can see is that the Gossify learning is very slow compared to Federated learning to other centralized schema. And the other algorithms are also good, but not as good as our proposition. And here, what I wanted to show is that one advantage of our approach is that we can choose the number of hubs in the network. So H is the parameter of the number of preferential connections, and it's when we choose the H parameter, we obtain at the end of the network with this number of hubs. So we can choose the number of hubs, and we can also choose S, the parameter, which is the number of hubs to which we send our model. And the idea that we can choose to have more hubs, so we are more resilient in case of failure, but we potentially we have more message are sent, so we need more bandwidth. And of course, we can choose the less hubs, but we are less resilient. So the idea that our algorithm is very flexible and adapts in a lot of situations. And as you can see, even when we change the number of hubs, the accuracy doesn't change a lot. It's almost the same. So the idea that even when we change parameter, the accuracy, the convergence to good level of accuracy is very very. And so for the learning part, we have also run some experiments in the crash, working in the context of crash. So for the crash 20 pairs case, in cycle 10, we have crashed 20 pair at random in the network. So we have 100 nodes in total, so it's 20%. For crash one hub and crash 5 hub, we have crash 1 hub and 5 hubs. So 5 hubs, it's all the hubs, but there's only 5 hubs in the network. So also in cycle 10, and as you can see, there is no impact because the hubs, there are new hubs that emerge after only 1 or 2 cycles. So the accuracy continue to go up. And we have also made a context where we have chance. So between the cycle 50 and the cycle 150, as I said, we have 10% of the nodes that disconnect the new nodes that appear. So the new nodes that connect to the network, they don't have any models. They start with the fresh models of random model. So they need time to get the average models in the network. And when we stop the churn, as we can see, the accuracy go up again, and it's fills the gap between the normal case. So to conclude, we have very good results in terms of final accuracy with time to converge to the global model. So almost the same as federated learning, which is our baseline, and much better than classic learning. And we are resilient to faults. And even in the case of faults, we maintain a good accuracy level. And now the next step I'm working on is to add more complex failure case, and especially Byzantine attacks. So we can imagine that some node will try to send false models to slow down the convergence to the global model. And we can also imagine privacy attacks where some nodes will try to get the data, to infer the data from the models. And also, for now, it's only simulation, so I want to test on real classical network. So to implement the algorithm in a real network. And also to try to have some mathematical background, because to prove the convergence to the topology with the hubs. And that's it for me. So
question on the last part, you consider various topologies of graphs, and you find different speed of I'm not sure I could call it mixing speed, but perhaps it's not the right thing. The topology of the graph has an impact on the speed at which your exchange of information between the various copies of the learning algorithm lead to something, right? Which is and the thing up there, one would be something equivalent to the non-federated learning, the learning on the old data, right? Am I right?
We have compared to the centralized scale, but in the centralized scale, we will have a very good accuracy already in the beginning. There is no cycle.
Yeah, but one is this. The accuracy is compared to the result for the.
One would mean that we don't have. I mean, the accuracy is the number of good predictions compared to the total number of predictions. So you do your learning on part of the data, for example, 90%, and you keep 10% of the data for the testing. So you test your algorithm on the remaining data, and you see if you have good predictions on your test data.
Okay, it's not the comparison of the decentralized with respect to the centralized. It's more just the accuracy on this. Okay. Right. But so my question is still valid, I think. What are the properties? You build a random graph in order to do the aggregation, if I get it correctly, right? And so what are the properties of the graph that make the convergence or the quality or the convergence to be fast or the improvement to be fast? And what others are properties of the graph make it slow? I would like to understand that.
Yeah. So there is the property of the graph, and so there is the property of the aggregation algorithm. But for example, gossip planning and epidemic planning, it's the same topology. It's a random graph topology. But in the case of gossip planning, we only aggregate with one node at each time. So I explained in some model to one node at one time. So it's totally asynchronous. In the opposite epidemic planning, we aggregate with all our neighbors at each cycle. So it's synchronous. We need to synchronize to have the schema, but it's faster. But for if we compare different topology, I think the main fact is from the diameter of the graph. If we have a small diameter, we converge more quickly, and also the number of connections. So we have only a few connections. We also converge more slowly.
But if it's the diameter of the graph that plays a role, what is the role of adding this extra? Because you had the hubs, right? And nodes were connecting to one of the hubs, or perhaps more, but you had the extra connections. So what is the role of the extra connections if only the diameter plays a role?
So here we don't use for the hill, so the hill algorithm, we don't use the extra connections for the learning task. But the extra connection are for to maintain the connectivity in case of if the hubs are disconnected. So if you are only connected to the hubs, if the hubs are disconnected, the network is disconnected. But thanks to the modern connection, we can emerge new hubs from the remaining nodes of the network and continue the aggregation.
Okay. So these extra nodes are not used in the aggregation. That's what you say, right? Extra edge. Okay. Thank you. And so the short answer is that this is really the diameter of the graph, which plays a role. Okay. Thank you.
And one other question.